This is a question from the book 636 on page 235. We've got this table of people's opinions on full body scans at airports and their political affiliation, and we want to see if these two variables are independent. First, we calculate the expected counts for these cells. Recall that the expected counts are the row total times the column total divided by the overall total. How many Republicans would you expect to not support the use of full body scans? That is the second row, first column. The row total is 170 times the column total, 318, divided by 1137, 47.55. How many Democrats would we expect to support? That's first row, second column. Row total is 914 times column total, 369, divided by 1137. The expected count for this cell is 296.63. And now, how many independents don't know? That is third row, third column, 53 times 450 divided by 1137, 20.98. I added part D. Let's perform a hypothesis test to determine if these variables are associated or not. Our null hypothesis is that they are not associated. A person's political affiliation is not associated with their opinion of full body scans in airports. Our alternative is that these two variables are associated. To perform a hypothesis test, we need to calculate the chi-square statistic, which means we have to calculate the expected value for every cell in the table, then subtract observed minus expected, square it, divide that by the expected count, and sum them all up. Even for a fairly small table like this, that's a lot of work. So it's good that we have R to do this for us. The data for this question is in the open intro package. I run the library command and the data looks like this. One variable that has their answers, one their party affiliation. So two categorical variables. I can run the table command like this, and I get a table that's similar to what we have up there, but in a different order. The order isn't going to affect anything, so I'll leave this as it is. Now I run the chisk test command on this table, and I get this output. The chi-square statistic is 4.3576. The degrees of freedom are 4. We have 3 rows and 3 columns. The degrees of freedom are number of rows minus 1 times number of columns minus 1. That's 2 times 2, so 4. The p-value is 0.3598. Since that's higher than 0.05, we fail to reject the null hypothesis at the 5% significance level. We cannot conclude that party affiliation is associated with opinion of full body scans. Another syntax I can use is this. If I tell it that X is one categorical variable, Y another, I get the same output. If I put $expected at the end of this CHISC test, it will give me the expected counts for each cell. And this gives you a quick way to check the assumption that your expected cell counts are all at least 5. And here's how the p-value is calculated. If the null hypothesis is true, this chi-square statistic follows a chi-square distribution with 4 degrees of freedom. This is where it lands on a chi-square 4 curve. The chi-square test is always a one-direction test. We always compute the p-value from the area ahead of the statistic, and that's this. The 0.3598 is this area. It's the probability of seeing a chi-square statistic at least as great as what we saw if the null hypothesis is true.